And hello, everyone. Hope you're all doing well. We only have a little bit left to lecture on here on osmotic pressure, and then playing around with some of these equations to calculate our molar mass of like an unknown compound. Um, and then we will be done with new material. So then we'll have an opening for you guys to ask questions on review and stuff like that. So your test for the last two chapters is this Sunday. So just make sure you get that done Sunday, Monday. Also, final will be next week. So make sure you are staying present with that. Let me pull up the syllabus. Just like you can't look at a syllabus enough. Okay, so yeah, your last test over chapter 10, 11, and 13, so gases, liquids and intermolecular forces, and then this final chapter on solutions will be running from Sunday to Monday. If you have any last labs, anything that you want to try and squeak in for partial credit, that all needs to happen this weekend. Okay, so go through, see if there's any missing mastering chemistries, any missing not exams, any missing labs, and I can try and give you some partial credit for it. Your final exam, it's set here, but the final exam will actually be on Thursday the 17th to Friday the 18th. Now, I wanted to just give you guys as much time as possible because that's the end of the semester, right? So I wanted to give you as much time as possible to study. If for some reason, if anybody in there needs to take this early, like you need to take it on Wednesday, or let's say all of your finals are packed on those last 2 days, I can work with you. Just send me a message. Otherwise, if it doesn't really bother you, just take it on Thursday or Friday. So we finished off last time talking about some of the colligative properties. So when you have a solution, and the more particles that you have dissolved in it, or this von Hoff factor, this I factor, the more particles you have, the stronger these colligative properties are going to be, or changes in these colligative properties. So when looking at these here, how we determine our I factor, well, if it's a non-electrolyte solution, non-electrolyte being molecular, we will give it a von Hoff of 1 because this thing doesn't break apart. If we're ionic, it means that this salt will break into its ions. So for this one, we'd get a sodium and a chlorine. So that would give us a von Hoff of 2. This one, we'd get 2 potassiums and 1 sulfate. Keep your polyatomics clumped. That would give us a total of 3. And then this guy down here, 3 of these ammonias and 1 of the phosphates would give us a total of 4. Now, if we have, so D, we would expect D to have the most effect on the colligative properties. A would have the least effect because it has the lowest I value. We looked at how it affected vapor pressure. So vapor pressure, if our, excuse me, I'm losing my train of thought here. Sorry. One of those days. All right, so the vapor pressure of a solution is lower than its pure equivalent. So the more junk you have, the lower your vapor pressure is going to be. Why? Because the junk sort of holds the solution in place. It kind of weighs it down. So lower vapor pressure with higher I value. We talked about boiling point and freezing point. And specifically boiling point elevation. So boiling point will increase. You'll have an increase in that if you have more dissolved salts. your freezing point is known as your freezing point depression. Freezing point will decrease as you increase the amount of particles. Gabby, no, I'm working. You can say hi.
Hi.
Okay.
Hi.
Okay, go. Please close my door. Sorry. And she sneaks in. So boiling point goes up, freezing point goes down. Let's look at the next colligative property, which is osmotic pressure. So what is, understand osmotic pressure, you need to know what osmosis is. So osmosis is the movement of your solvent from a high solvent concentration area to a low solvent concentration area. Or it's the movement of the solvent from a lower solute, a more diluted solution, to a higher solute or a higher concentration solution. So if I have, two chambers and one of them is really salty and the other one is not very salty, and there's a connection between the two of them, the water will move from the less salty tank to the more salty tank to balance out or equalize the concentration. So osmotic pressure then is the pressure required to stop osmosis from happening. So there's going to be this natural flow of, if we're talking about a water solution, there's going to be this natural flow of water from the more diluted to the more salty. If I try and resist that flow, that will be equal to our osmotic pressure. Now, how does this relate to the amount of particles that we have? Well, if we have more particles, so increase in particles. Or we can also say an increase in our I value, our von Hoff factor. That is going to equate to an increase in our osmotic pressure. So the more particles that are in solution, the more concentrated the solution is, the quicker there's gonna be this sort of equalizing or flow of the solvent. And if it's moving quicker, if the solvent's moving quicker from one tank to the other, the resistance to it, or the osmotic pressure, will also have to increase. And this is the equation that we use for it. Now, pi over here is not talking about 3.14. Okay, pi is talking about the osmotic pressure. And this is specifically in units of ATM. So how much pressure needs to be applied to stop this flow? Your osmotic pressure equals your von Hoff factor, your I factor. So, the more particles you have, the bigger this osmotic pressure is. Those are directly related to each other. So it's your I factor times, and actually let's look at this one over here real quick. It's your I factor times your molarity, which remember is moles over liters, times R, and R is the gas constant. So 0.0821. T is temperature. Can I make it bigger? Yeah. Actually, let's not annotate. Let's write in the document itself. Okay, so osmotic pressure, so increase in particles or an increase in I equals an increase in our osmotic pressure. So pi is the osmotic pressure in ATM. R is our, or we said we've got I is our von Hoff, M is our molarity, R is our gas constant, and then T is temp.
Temperature in Celsius?
Temp is going to be in Kelvin. Molarity is going to be in moles per liter. No unit on the I. Gas constant, remember the units on the gas constants are ATM, liter, mole, Kelvin. So if gas constant is in zero, let me write that out, 0.0821 ATM, liter over mole Kelvin. If those are the units we honor for the gas constant, everything else has to fit into those units. This equation here, this one in the middle, is very similar to this one. They've just expanded out molarity into moles per liter or N per V, okay? So you may be given molarity or you may be given moles and liters. Don't get freaked out. You just would use this intermittent one. So let's try a problem with this. We're looking at blood pressure. And it says the average osmotic pressure of blood is 7.7 ATMs at 25 degrees Celsius. What concentration of glucose will be isotonic with blood? And isotonic just means balanced with. So we have information on everything but concentration, which is our molarity. So I would use the pi value is equal to the von Hoff M R T. And we want to get M by itself. So M is going to equal our pi divided by our von Hoff times our R times our T. So osmotic pressure is given to us as 7.7, and that's an ATM. So we like that, 7.7 ATMs. Our von Hoff, what is our von Hoff number for glucose? Looking at that, is that an electrolyte solution? Does it form ions? Will it break apart? No, it's completely molecular, right? So everything in there is a non-metal. So that glucose molecule is going to stay clumped together. So we're going to give ourselves a von Hoff factor here of just 1. Our R value we said was our gas constant. So 0.0821. I'll write in all the funky units. So why not? Come on. ATM, liter, mole, Kelvin. Okay, and then the last thing we want to do over here is multiply by our temperature. Now temperature needs to be in Kelvin. So we want to just real quickly add 273 to our 25, which would give us 293, I believe, 298. 298 Kelvin. All right, so looking at what units will cancel here, ATMs and ATMs cancel, Kelvin and Kelvin cancel. And so we have liters divided by moles, but that whole thing is under the fraction bar. So we have to, so we'll inverse it. So we'll end up getting a unit of moles divided by liter, mole over liter, which is in fact molarity. That is our concentration. So that's one way to confirm that you've plugged it in correctly. So when we enter all this stuff in there, we get a value of 0.0 0.315 moles per liter, or you can write it as 0.315 big M. And specifically that's glucose. Now, a couple things to note: if osmotic pressure had been given to you in, say, torr, you would need to convert it, all right? If the problem instead said something about not what is the concentration of glucose, but like how many moles of glucose are there, you would have to have been given your values of liters to be able to convert. You needed another piece of information. So all of these colligative properties we can use sometimes to figure out the molar mass of an unknown concentrate or an unknown solution. So if I've got, let's say it's glucose, but I don't know it's glucose, but I know all this other information about it, I can work backwards to figure out what the molar mass is and determine that the dissolved solute would in fact be glucose. So let's try out a couple problems with that. There's a bunch of different types of problems. So you've got to kind of use your critical thinking skills on what am I looking for. So for molar mass determination, let's remember what molar mass is. Molar mass is equal to moles over, or I'm sorry, grams per mole. My bad. I'm like wanting to go moles per liter. I don't know why. So molar mass is equal to grams per mole. So in a lot of these problems, you'll be given like one of these and you got to figure out the other one. Usually you're given this thing here. You're given the grams and you need to somehow find the moles. And a lot of these equations relate things like molality, which have moles in it, or molarity, which have moles in it. So in this equation here, it says a solution of an unknown non-volatile, non-electrolyte was prepared by dissolving 0.250 grams of the substance in 40.0 grams of CCl4. So we've taken an unknown solution or an unknown solute and dissolved it in 40 grams of the solvent. It tells us the boiling point of the resultant solution was 0.357 degrees Celsius higher than that of the pure solvent. Calculate the molar mass of the solute. So we want to figure out molar mass. I actually already know the grams of it. It says that we dissolved 0.250 grams. So I'm going to plug that in to my equation over here. I've got 0.250 grams of this unknown solute. What I need to calculate are my moles of this solute in solution. Now, how do I get moles? Well, with these equations or with these problems, I would look at what is it talking about? It's talking about a change in temperature. It's talking about Kb. So I'm going to write that equation or the change in my boiling temperature. So we're saying change in boiling temperature is equal to our Kb value times little m, which is molality, times I. So which one of these values has moles hidden in it? This thing right here. Because what is molality again? Molality is going to be equal to moles of solute divided by kilograms of solvent. So do I know the other things in order to find that little m? Do I have change in temperature? I do. It's given to us in the problem, 0.357. Do I have Kb? It wasn't originally written in there. I had to fill it in, but you would have to be given that. Okay. So we've got our change in temperature. We've got our Kb value right here, and then we need our von Hoff factor. So what is our I value? Well, this says it's a non-electrolyte. Non-electrolyte means that it's a factor of 1, right? So I will equal 1. For all these molar mass determinations where it's unknown, if it doesn't explicitly tell you the I value, you can just assume that it's 1. Right. So now we just get to plug and chug. So we're going to solve for molarity, or molality, rather, molality. Let me get I'm going to temporarily erase this so we got some space. So we know our change in temperature right here, 0.357, and this is in degrees Celsius. This is going to be equal to my KB value, which I am saying is 5.02. My little cursive m, molality, is unknown, and my von Hoff factor is, in this case, 1. I get 1 particle in a non-electrolyte. So if we can re-isolate for our m value, our little m value, this guy here, we find that little cursive m is going to be equal to 0.0711. Now, what are the units on this thing? Well, it's this thing is equal to moles of our solute all over kilograms of solvent. Do I have either of these values? Actually, I do have this bottom one, not quite in kilograms, but I have it in grams. And I want this moles of solute, right? At the end of the day, what was I trying to get? I was trying to get my number of moles to plug into my denominator. So here I can leave this as moles of solute, and then in the bottom, I can fill it in with this value converted into kilograms. So move the decimal over 1, 2, 3. So now we have, instead of kilograms, we have moles of solute divided by 0.040 grams of the solvent, or what it's getting dissolved in. If I multiply this over here, I can figure out my moles of solute, right? So moles of solute in this case will equal 0.0000284 moles. So I used my colligative properties to figure out the moles. Now I can take the moles and just thread it back into this equation over here, 0.00284 moles. Take the grams over mole. The units won't cancel, which is good because we want grams per mole in order to calculate molar mass. And I'll get 87.9 grams per mole. So now I know what my molar mass is of this unknown material. Now, if they had given you, hey, it's one of these 5 things, you could calculate the molar mass for each of them and match it up. But in this problem, it just is saying, just tell me what the molar mass is. So I want you to try another one of these right here. It says a solution containing 10 grams of an unknown liquid and 90 grams of water has a freezing point of negative 3.33 degrees Celsius. Now, this is talking about a water solution, so we can assume that the normal freezing point of water is 0 degrees Celsius. Now it's negative 3.33 degrees Celsius. The KF value is equal to 1.86 degrees Celsius per little cursive m, that's the unit on it, for water, and the solute is non-electrolyte. What is the molar mass of the solute? So this is a similar problem to the one we did previously, but this is asking you for K. This is giving you information on freezing, on KF and stuff. So shouldn't be that much of a stretch. So I'll give you all 5 minutes or so to work on that. If you have questions, you know what to do. So looking at this one, this is another problem where you're given a bunch of information and it really just wants you to calculate molar mass. So writing out or reminding yourself that molar mass is going to equal moles of your solute divided by, I don't know why I keep wanting to do that, I'm sorry, mass of your solute. Or grams of your solute divided by moles of your solute. So grams over mole or gram per mole. Do we know grams of the solute? We do. That information is given to us right here. So right off the bat, we can just plug that in. We need to calculate moles of solute. So I'm given a bunch of information about KF and temperature change. So I'm going to write out the equation that's associated with that, which is that my change in temperature freezing is going to equal my KF times my molality times my I value. My change in temperature is negative 3.33. We can ditch the negative here, just go with the absolute value. So 3.33 is going to be equal to this KF value, which is given to us right here, 1.86. The units on that are C over M if you're interested. Molarity or molality I'm trying to find. And then my I value, it says it's a non-electrolyte solution. So it should have an I value of 1. Again, with these problems, it's usually just going to be a value of 1 for that. So we need to solve for molality because molality is the only thing in here that remotely gets close to moles. So I can rearrange and figure out that molality in this case is 1.79. And remember, molality is equal to moles of solute over our kilograms of solution, or sorry, kilograms of solvent. So if I have this value and I want to solve for this value to get it back in here, right? Because this is the same thing as this, we need to figure out our kilograms of solvent. Do I have that? Well, I have grams, so pretty close. So I can plug in for this bottom value, 0.090 kilograms of my solvent. We just take that and multiply it over times the molality, and we'll get moles of our solute is equal to, I got it worked out for you guys, 0.161 moles. The final step is to take that mole value and then just plug it back into that original equation, which tells us our molar mass, 1.161 moles. Both units will come with us. We like that. And we get 62.1 grams per mole. Now, there are quite a few compounds that have a molar mass of 62.1. So you wouldn't be able to just come up with its identity out of thin air. You'd have to be given like a couple different options. But again, in this problem, it's just asking for the molar mass. Let's look at another one of these problems, solving for molar mass, but we're going to be given different information. So it's not going to be based off of temperature and boiling point. It's going to be based off of osmotic pressure information. Okay, so in this problem down here, it says the osmotic pressure of an aqueous solution of a certain protein was measured in order to determine the protein's molar mass. Okay, so we're trying to find molar mass. It says calculate molar mass of the protein. So I'm going to write molar mass, and I'm going to say that it's equal again to grams over mole. The solution contains 3.50 milligrams of protein dissolved in a sufficient water to form a 5.00 milliliter solution. All right, so what can I pick out of there? Well, I know how many grams of protein I have. So I'm going to put that in right off the bat, 0.0, well, milligrams, 1, 2, 3, so 2 zeros, 0.00350 grams. As with most of the problems, I'm going to need to find my number of moles. We have a volume amount. It also tells us the osmotic pressure of the solution at 25 degrees Celsius was found to be 1.54 torr. Calculate the molar mass of the protein. So this is talking about osmotic pressure. I'm going to want to go with my pressure equations. And we had 2 of them, and really you could use either one. We could use, we've got our osmotic pressure, pi, is equal to my I value times my molarity times my R times my T. You could use this one, solve for your molarity, and then divide it by the volume. Or we could use the other equation, which is I times moles over liter times my R value times my temperature. Now with this equation, because we're using that R value, we are constrained on what the units can be. So if you notice, our osmotic pressure is given to us in torr. It says 1.54 torr. I need to be in ATMs, so let's convert that. 1 ATM is equivalent to 760 torr. Right? Or we have a pretty small osmotic pressure of 0.00203 ATM. Okay, so that's this here. This whole thing equals I times mole over liter times R times T. I is our von Hoff factor. It doesn't tell us anything else outside of it being a protein. So if it doesn't tell you your I value, assume an I value of 1. And a protein is in fact going to have a von Hoff of 1 because it's a molecular compound, so it doesn't break apart into ions. Do I know my moles? No. I'm trying to find moles. Do I know my liters? I actually do know my liters. Well, I know my milliliters, but I can convert that into liters. So 0.00500 liters. My R value is a constant, so that's always going to be 0.0. Oh, come on. And then liters, ATM, mole, Kelvin. I have then my temperature. Now, because R is in Kelvin, my temperature is also going to need to be in Kelvin. So we're going to take that 25 and add it to 273 or get 298 Kelvin. So from here, we plug in, the one thing I missed here, let's put this as a 1 instead of an I. Put that as a 1. So when I isolate out for moles here, that's the only thing that I need, I end up getting 4.14 times 10 to the -7th moles. Again, you could have plugged this in to this one, solved for molarity, and then just taken that and divided by your volume. That would have worked as well. The last step is to take this and plug it into our original equation of grams over mole. We know our grams, 0.00350. If we now know our moles, 4.14 times 10 to the -7th moles. These are tiny numbers, both of these. I end up getting 8.45 times 10 to the 3rd grams per mole. Or that's 1, 2, 3. That's the same thing as saying 8,450 grams per mole. And you may be thinking, that's a really big molar mass. Proteins are huge molecules. Okay, so it's not uncommon to see something that large for a protein. Proteins will be a bunch of molecules sort of chained together in these like really long polypeptide chains. So we would see that. So, you know, if the problem is saying determine the molar mass and it's giving you a bunch of information that doesn't seem like it has anything to do with moles, play around with these equations and see how you can get close to moles. So molarity, isolating for molarity is a great way to get moles. Isolating for your molality is a great way to work towards moles. All right. Questions on those?
Can you scroll down again so I can see the answer?
Mhm.
And then why were you, I guess I got 8,436. At what point were you?
8,400. You got 8,436. My guess is it's just rounding. One of us had a rounding issue. It wouldn't be detrimental. You'd be able to come up with the right answer. Try. Yeah, I got 8,454, but 3 sig figs would get us to 8,450. But if you're at 8,435, you're close enough to get the answer. So, yeah, so that's it. That's the semester. That's all the information that you need to have in your brain. Yay! So anything you guys want to go over, look at, try out, doesn't have to be isolated to this chapter. It can be, you can reach back. You just gotta let me know. Nothing. Everybody's in it. You're all experts. I hope so. Okay, well, I will be, I'll be hanging around for a couple minutes. So if you guys want to go through your notes, you want to flip through some stuff and then holler at me, I'll just be hanging out here. Otherwise, if you're good to go, you're good to go. I will be offering a review on Monday as well, because it's only Tuesday, right? We're only Tuesday. Okay, I'll be offering a review on Thursday. So if you're like, I don't have my stuff together, get your information together so that we can do this final review on Thursday and do it effectively and efficiently. All right. Otherwise, you're more than welcome to stay around here. We'll be sitting around. Yeah, that's all I got.
So we have everything we need now to complete all of our mastering chemistry
should have everything you need to complete all the mastering chemistry. You should have everything you need to complete any labs. You should be able to take all exams and you should be able to take the final.
Thank you.
Yeah, you're welcome.
See you soon.
Yep. Bye, David.
I'm trying to find where we started talking about molar mass in our notes. Was it before this stoichiometry solution dilution? Or was it after?
Yeah. Yeah, hold on one second. I'm going